Hello children, here we are coming from my fabulous kitchen. I had to move in here from my office because I spilled my Diet Coke on the floor. Alright, we're going to start heat. And I've already put a video on Classroom that has a professor explaining how the thermometer, how Fahrenheit came up with his temperature scale, and I'm going to probably go through that as well as I go through this, but that you don't have to watch that. It's just kind of up there if you want to. I've always thought it was very interesting. It's something I found maybe the first or second year I was teaching and thought, oh, I wish I'd known that a long time ago. Okay, so let's start with chemistry of heat. First of all, heat is a form of energy. You guys should have at some point gotten different forms of energy in middle school. Lots of different forms. Chemical energy, which is the energy that comes from breaking bonds. We have mechanical energy, which is energy something has because it's in motion. We have nuclear energy, which is the energy when a nucleus either breaks apart or is fused together. Breaking apart a nucleus is called fission, and putting a nucleus together is fusion. We have electromagnetic, which deals with the movement of electrons. And then we have what we're going to talk about now, which is thermal energy. Which is the total energy of all particles motion. So we could put kinetic energy in there, because kinetic energy means energy from something that is in motion. It's the total sum of the motion of all the particles in a substance, and that's important. Now, a lot of times, the first thing you think of when you think of heat is temperature. And temperature does measure the motion, but it's the average kinetic energy. Oh, it said of particles in an object. It's the average kinetic energy. So it's the average movement of the particles, but it doesn't take into consideration how many particles there are. Heat, you have to know about the particles. Temperatures don't measure heat, they measure motion. Okay? Now, if you watch that little video, they'll explain this. Again, I'm going to explain it. If we stop and think about temperature, we have three main types of temperature scales that we are used to using. All right, the first one is based on absolute zero. Okay, and this is the Kelvin scale. The definition, absolute zero, is the temperature at which all molecular motion stops. Okay, so zero is down here. Freezing point of water is 273 Kelvin. Okay? That Kelvin used information about gases. We're going to do gases next. Basically, he knew that as gases volume gets smaller, the temperature will go down, or as temperature goes down, the volume gets smaller. There's a direct relationship there. And he was able to extrapolate how that temperature was changing as the volume changed and came up with Kelvin. Now, you all are familiar, of course, with Fahrenheit. Fahrenheit, we know that the freezing point of water is 32 degrees. The boiling point of water is 212. Boiling point in Kelvin is 373. And 0 on the Fahrenheit scale is the freezing point of brine, which is basically salt water. Okay? Now, how did he come up with that? He had actually gone to visit somebody who made thermometers, and he used some of his information, and he set 96 as body temperature. And then he set 32 at freezing point of water. Now, if you take 96 minus 32, that is 64. 64 can be divided in half, in which you get 32. 32 can be divided in half, in which you get 16. 16 can be divided in half, in which you get 8. 8 can be divided in half, in which you get 4. 4 divided by half, 2. 2 divided by half, 1. So it was very easy to take that 2 and go, all right, well, here's freezing point of water, here's body temperature, and then using instruments, etch onto the glass of the thermometer the degree markings. And it was very simple because you could measure what was halfway between the two, what was halfway between those two, and come up with your degree size. Okay? So totally the reason he did it was because it made it easy to make the instrument. All right? 32 down to 0, same story. 32 divided by half is 16, and so on and so forth. Okay? The third temperature scale is Celsius. It sets 0 for the freezing point of water, and it sets 100 for the boiling point of water. Okay? So if you're talking about Kelvin, there are never any negative numbers. This is perfect for scientists. Because if you're talking about volume, and you have a temp of a gas, you want to have positive numbers because you can't have a negative volume. All right, Celsius does have negative numbers, but Celsius is really useful for things like baking and cooking because Celsius is based on the freezing and boiling point of water. And most of the time, if you're baking, you're going to be warmer than 0. And Fahrenheit is perfect for weather, because we generally don't see temperatures below 0 except for maybe 1 or 2 days of the year. And we don't see temperatures that are at 212 ever, hopefully. All right, so that is where we get the temperatures. All right, so back to this question. Lord Kelvin used information about gas volume. No, we already said that. We're talking about now which contains more heat. Now notice our vocab. Here we have heat, here we have temperature. Let's go back to the definition of heat. Heat is the motion of all of the particles. So here we're talking about a bathtub versus a coffee cup. The coffee cup has boiling water. The bathtub has water that's 50 degrees Celsius. The question is, who has more heat? Well, believe it or not, the tub does. Even though it's a lower temperature, it has a larger mass. So it has more heat. Which has the higher temperature? Well, the coffee cup has the higher temperature. how do we convert those? This isn't something I'm going to ask you on a test, but if you should ever go traveling to another country, you're probably going to be given temperatures in Celsius. When I student taught in England, I had every morning I'd get up and listen to the forecast, and I had to learn that 10 degrees didn't mean I had to bundle up. 10 degrees is 50 degrees Fahrenheit, 10 degrees Celsius. So I knew I needed a jacket. So if we want to make conversions from Fahrenheit to Celsius, you take your Fahrenheit temperature and you subtract 32 from it. Then you multiply that times 5/9, and you get your Celsius temperature. Okay, so I know that 50 degrees, if I subtract 50 minus 32, that's 18. 18 times 5 divided by 9 would be 10 degrees Celsius. 50 degrees Fahrenheit, 10 degrees Celsius. To go the other direction, Celsius to Fahrenheit, you take your Celsius temperature and multiply it by 9/5 and then add 32 to that. So if we have, say, 23 degrees Celsius, well, let's go 25 because math will be easier. 9 times 5. Why can't I do that in my head? 45, right? 45. And then we have to add 32 to that. 5, 6, 7, 4, 5, 6, 7, 77 degrees. 23 degrees is generally considered room temperature, so 25 would be close, a little bit warmer than 72, 73 degrees, and that's what we get. All right. You can't do math in your head. COVID 2020. All right, Celsius to Kelvin, we take Celsius, add 273 degrees to that, and we get Kelvin. All right. Now, so we've established the difference between heat and temperature. If we want to figure out how much heat something has, we need to know how much of it we have, which is the mass. We need to know what kind of temperature change we want it to make. We call temperature change, we use the triangle, which means change. We use T for temperature. So we need to know the mass. We need to know what kind of temperature change we're going to need. But we also need to know what it's made of. Stop and think for a moment. If you're outside and you have a metal piece of metal on the ground and a puddle of water, which is going to have a higher temperature on a hot sunny day? Well, the metal will heat up much easier because of what it's made of. So we have to have that other piece of information, and we call that specific heat capacity. That is the ability for something to heat up. All right, and our specific heat capacity is defined as the energy needed to raise the temperature of 1 gram of substance by 1 degree Kelvin. Okay, 1 gram by 1 degree Kelvin. And if you look, copper has a specific heat of 0.387. Glass is 0.840. If we get down here, ethyl alcohol 2.45, glycerin 2.41, water is 4.18. That's a number that you're going to need to learn. I mean, you don't have to have it memorized, but you're going to use it, so you might as well. And notice that mercury has a very low specific heat capacity, meaning that it will change, the temperature of it will change very, very easily. You don't have to add much energy. Whereas water, you have to add 4 joules to get 1 gram of water to go up 1 degree Celsius. Okay? Now my daughter coined this MCAT. Change in temperature, mass, C for specific heat. The equation in your worksheet here uses C sub P, which is what Clement uses. I've seen it used SH. There's lots of different ways. We're going to use C because it works with our little mnemonic. And what does that add up to? That adds up to heat. And what do we use to abbreviate heat? It makes so much sense. We use a Q. Q equals MCAT. It makes no sense at all. Okay? Although you could kind of make a cat here, and there's his tail. All right. So this is the equation we use for calculating heat. We use the mass times the change in temperature times the specific heat capacity. And remember that specific heat capacity is basically what is it made of. If it heats up easily, it's going to have a low specific heat capacity. If it heats up slowly, it's going to have a high specific heat capacity. All right, so let's throw that in. All right. So first, calculate the heat change. Oh, let's talk units. The units for specific heat capacity. It's the energy it takes to raise 1 gram of a substance by 1 degree Celsius or 1 degree Kelvin. So these are our units for specific heat. Our units for heat are joules. You can also use calories, but we're not going to worry about calories. All right. Calculate the heat change when 500 grams of iron is cooled from 100 to 22 degrees. Okay, what's our mass? We're going to use Q equals MCAT. Our mass is 500 grams. The specific heat of iron, which happens to not be in this little table, is 0.45 joules over grams degrees Celsius. And the temperature change, it's cooled. We always go, temperature change is going to be temperature, the final temperature minus the initial temperature. So we're going to take 22 minus 100. And that is a difference of 78. If we multiply those all together, of course I didn't do it in advance, 500 times 0.45 times 78, negative 78, we get negative 17550 joules. That negative means it's given off. It's exothermic. It's being released. It cooled down, so it gave that energy had to go somewhere. It was given away. Calculate the heat change when you have 500 milliliters of water. For this, we have to remember that when you have water, 1 gram of water will take up 1 milliliter. So 500 milliliters means 500 grams. 500 grams of water. Our specific heat of water is 4.184. That is up here in our equation. And our temperature change here is going from 22 to 100. Again, it's cooled. So we're doing 22 to 100. So again, it's at negative 78. So 500 times 4.184 times 78. It is going to give off 163,176 joules. So a chunk of iron or an amount of water that are the same, which is going to heat up easier? The iron, because it's taking less energy to heat up. Which is going to take more energy to heat it up? The water, because it has a higher heat capacity. All right, we'll stop there for today.